Hello geometers. This video is about remembering what we know about special right triangles and using that information to find the area of an equilateral triangle and then of a regular hexagon. So first off, we need to remember what is it we're supposed to know about special right triangles. Well, special right triangles refers to two particular right triangles, a right triangle that has angles of 30, 60, and 90, and a right triangle that has angles 45, 45, and 90. This one, notice because the angles are the same, we're talking about an isosceles triangle. So this is also sometimes just referred to as a right isosceles triangle. The two legs are congruent. So these are triangles that come up so frequently in other situations that we have basically just memorized the ratios between the side lengths, how the side lengths relate to each other. For the 30, 60, 90, I'm going to go ahead and call the shortest leg, or the shorter leg, we just sometimes say short leg, X. Now remember, the two legs of a right triangle are the two sides that meet at the right angle. So that's what I mean by legs. The other side is the hypotenuse. Now the short leg is going to be across from the smallest angle. Remember that in every triangle, the shortest side is across from the smallest angle, and the biggest side or longest side is across from the biggest angle. So this is my short leg. Short leg times square root of 3 gives me the long leg. So here's the long leg. Going back to short leg, both of these rules come from the short leg. Short leg times 2 gives me the hypotenuse. So the rule helps me get from the short leg to the hypotenuse, or from the short leg to the long leg. There's not a rule about how to relate the hypotenuse to long leg or vice versa. We always get the short leg first if that's not where we start. So for instance, if I started with the long leg, now I'd have to go backwards. The times root 3 is coming from here. X times root 3 gets me here. So going backwards, I would divide by root 3. Same thing going here. From hypotenuse to short leg is dividing by 2. Down here on a 45, 45, 90, we have whatever one leg is, the other one is also the same thing. So how to get the hypotenuse from either leg is I'm going to multiply by square root of 2. So either leg times square root of 2 gives me the hypotenuse, which means if I started out with the hypotenuse and wanted to go backwards, in other words, find a leg length, I would have to get smaller, so I would divide by root 2. So one thing I tell my students is basically, you only have to remember 3 numbers. If you're going back and forth between the short leg, that's root 3. So short leg to long leg, or backwards, root 3. If you're going from the smaller one to the bigger one, you multiply by root 3. Bigger one to smaller one, you divide. Short leg to hypotenuse, the number to remember is 2. If you're going from short to hypotenuse, you multiply by 2. Hypotenuse to short, you divide by 2. And then in a 45, 45, 90, you don't have short leg. You've got two legs that are the same. So this is from either leg to the hypotenuse. You use the number root 2. If you're going from a leg to the hypotenuse, you multiply by that. Going from the bigger side to the smaller, the hypotenuse to the leg, you divide by it. Okay, so in context of what we're looking at here, what does that have to do with anything? Well, we're specifically looking at area of an equilateral triangle, area of a regular hexagon. Okay, so let's look at an equilateral triangle. And I'm not going to draw an equilateral, I'm sure. It's not going to look perfect. But let's pretend that it's pretty close. Actually, it's pretty close. Okay, you draw enough triangles, you get pretty close. Equilateral triangle means all the sides are the same. So let's suppose for a moment that, for instance, my side length is 8. Okay, now that means this side's also 8 and this side's also 8. Well, if it's equilateral, it's also equiangular, meaning all 3 angles are also the same. So if I have 3 angles, and we know that they have to add up to 180, if they're all going to be the same, that means they're all 60. So if I want to find the area of a triangle, I usually use this formula. Area equals 1/2 base times height. The problem here is that I don't know the height. So this is where the 30, 60, 90 comes in. If I draw an altitude, any one of the altitudes, what it does, and remember an altitude goes from a point, a vertex, to the opposite side such that it makes a right angle. But because this is an equilateral triangle, it's going to divide it into two identical 30, 60, 90 triangles. Remember, this whole angle up here was 60. Just one side of it now is 30. So this is a 30, 60, 90 triangle. The short leg is down here because it's across from the 30. The long leg is right here. That's the height that I need in my formula. And the hypotenuse is 8. Okay? Well, if this whole distance here is 8, then the short leg here is 4. You could also find that because hypotenuse, remember, divided by 2 gives you short leg. So short leg here is 4. Short leg times square root of 3 gives me long leg. So that means this is going to be 4 root 3. And now I have the information I need to be able to find the area of this triangle. 1/2 base times height. Now remember, we split it in half to get the short leg of this triangle here, but the whole base of the triangle, the big triangle, the equilateral triangle I'm trying to find the area of, the base is 8. So 1/2 of 8 times the height, which is 4 root 3. And that gives me 1/2 times 8 is 4 times 4 root 3. That's 16 root 3. That's my area. Okay, now let's look at a regular hexagon. And I'm not really loving this graph paper. I feel like it's a little bit harder to see on. So I'm going to see if I can switch to doing it on here. Regular hexagon, 6 sides. The fact that it's regular is just saying that all 6 sides have the same length and all 6 angles have the same measure. Okay, so if one side of my regular hexagon is, for instance, let's go with 8 for right now, then all of the sides are 8. Now the nice thing about a regular hexagon is, if I were to draw these lines, they're actually still called radii, just like they are in the circle. If I were to draw them all, I've divided a hexagon into 6 equal, identical, congruent equilateral triangles. And that's always true for a regular hexagon. A regular hexagon can always be split into 6 identical equilateral triangles. Well, if it's equilateral, and I know that this side is 8, well then this side is 8, and this side is 8, and hey, we basically have our equilateral triangle we just did. So the height of this is going to be 4 root 3. I'm going to do exactly the same stuff I just did. So whatever I got for the area here is what I'll get right here. So I'm going to write it inside the triangle. It's 16 root 3. But I have 6 of them. So this is also 16 root 3, and this is 16 root 3, and so on. So basically 16 root 3 times 6. And that would be, let's see, what's 16 times 6? I should know this, shouldn't I? 96 root 3. There it is in exact form. That's the area of that hexagon. Now I'm going to go ahead and, let's see, I'm going to try to erase just the stuff here. I don't even know if I wanted to do all of that. Let's do a different length, a different side length. I used the 8 just because I wanted to show you that it's literally exactly the same as that equilateral triangle we just did. But let's say that my side length is 10. Okay, so now I'm going to look at this equilateral triangle here, just pick any one of them, and I'm going to look at it and I'm going to say, okay, if this is 10 and it's equilateral, then if I drop an altitude right down the middle, this is 5, this is a 30, 60, 90 right over here on the right, and this is the 30, this is the 60, this is my short leg times square root of 3 gives me the long leg. This is the height of the triangle. So now I have 1/2 base times height is 1/2. Now, this is not the base. This 5 is only halfway across the base. The base is still 10. So 1/2 10 times 5 root 3, which is 5 times 5 root 3, or 25 root 3. Now that's the area of one triangle, right here. I don't know if I made that clearer or yuckier, but that's the area of that one triangle. So if I want the area of the entire hexagon, I'm going to do 6 times 25 root 3, and that's 150 root 3. And that's the hexagon's area. Ta-da!